So, friends, welcome to this lecture series of geomorphology, and in this class we are going to discuss about the wind system dynamics, the wind velocity dynamics, the availability of the sand, how this wind dynamics and the availability of the sand, availability of the loose material, it is creating some of these peculiar landscapes. So, suppose we have a length of sand sheet and we allow this wind to blow on it. With time the thickness increases or decreases. This material, at what speed the material will start saltating, and if the saltating grain is impacting on this another saltating grain, impacted grain, how it will behave, and finally with more and more saltation this wind becomes saturated with the sediments, and finally the system will move, the layer will move and creating a ripple, and with more and more addition of this sand, this whole system will move forward and new landforms will form. Strong winds create surface velocities over hard surface that can transport sand grains downwind. Over sand, however, this wind energy near the surface is absorbed by saltating sand, and the new sand derived from the upwind is deposited in increasing amount until an equilibrium is reached with the amount leaving from this patch. So, that means suppose we are allowing this wind speed to be more. So, material removed from here, at the same time material is added here. So, that will continue up to this equilibrium is reached of the removal material and the addition of material. So, here it is a figure shown the descending grains, suppose a grain is saltating here and descending down, here it hits the surface. So, once it hits, it hits out 2, 3, 4, 5 grains or number of grains, and those grains they are started saltating here, and once these 3, 4 grains again add here, that will create again saltating more number of grains, again the same material it is coming, again it will saltate more number of grains. So, that means in the downwind directions, if the wind velocity or the wind speed continues like this or increases like this, in the down wind direction, more and more sand will be added to this wind, so that the wind will be saturated with the sediment content. So, if you see here rapidly increasing saltation, saturated boundary layer. So, that means here this is a saturated system, here wind is more and more sand grains is added to the wind system. For net accumulation to occur on an exposed sand patch, it must have a minimum initial downwind length of about 4 to 6 meter, several times the length of the saltation trajectory. So, now you see, suppose this is a sand surface and we are allowing this rock or allowing the wind to move. So, it will pick up a sand grain here and it will put it here. So, this is the length of saltation or saltating wave. But here accumulation, when we talk about deposition, we are talking about the accumulation. So, this removal of this material to deposit, we need a critical size of a sand body, and that critical size is 4 to 6 meter. So, that means if we have a sand sheet spreading about 4 to 6 meter length, so material can be removed here, and due to saltation it will be hit here, and it will create some material, again it will finally the wind will be saturated and deposition starts at the end. So, if it is less than the critical size, then simply it will remove and it will move this sand from one place to another place. So, that means deposition within the sand body, it occurs only and only if it is of a more than of a critical size, and for here the critical size is about 4 to 6 meter. Then the simplest depositional form or the smallest and simplest depositional form of a wind is called sand ripple. Like water ripples, wave ripples, similarly we have sand ripples also. wind ripples develop transverse to the wind directions. Here if it is wind is blowing from here to here, this is yellow arrow is shown, and these are these wind ripples, these are the sand ripples, and the sand ripples if you see by cross section it is asymmetrical shape. Here this is the wind direction and sand is being transported, and here if you see if you are moving from bottom to top, the coarseness of the grain increasing. So, that means here this is called a brink point, and this brink point this free rolling is there, free rolling of this, because this grain is placed here more than the angle of repose. So, that is why there will be free fall and will be deposited here. So, that is why the 4 sets are formed in these positions. So, now this upper part of this ripple is occupied by coarser material as compared to the lower part. This is due to deflation effect. By deflation, the smaller particles will be removed and this larger particles or the coarser particle will be remain at the top. So, this is due to deflation effect, the surface of a ripple or the top part of a ripple is occupied by the coarser material, and gradually the size decreases. A smooth sheet of sand is inherently unstable under gentle wind. The saltation method of sand movement results in most grains of this given size following trajectory of similar length. At the upwind edge of a sand patch where transport first begins, a lag of coarser grains is left behind. So, that means we have a sand sheet, it starts from here and the deposition will occur if it is of more than of the critical size of 4 to 6 meter. So, from here once this saltation, suspension, creep it occurs. So, in this area will be enriched with coarser material and the finer material will be removed from this position and will be deposited here. So, by this way we can distinguish the sorting, two different sorting characteristics of material produced here. The saltating grains moving downwind from that lag area impact at the mean distance of saltation and produce another lag area. So, once the saltating, suppose for example saltating starts here and it comes here and from here it is coming here again coming here. So, by this way progressively lag area is being created. So, that is why this area will be occupied by more coarser particle, finer particles gradually increases to this area. Okay. So, by this process wind ripples develop transverse to the wind directions, transverse to the wind direction. If you see this is the ripple axis, this is the ripple axis. So, this is the wind direction. So, it is transverse to that. So, their typical wavelength is about 1 meter or less, very similar to this characteristics flight length of the saltating grain, but probably more influenced by statistical fluctuations in the scatter of impacted grains. Here impacted grains plays major role. For example, suppose one grain is picked up from here, its saltating is here, but once it impact here 3 to 4, 5 grains they are again saltated. So, again that 3, 4, 5 grains again saltate number of grains. So, that means this typical wavelength of saltation equal to 1 meter or less, very similar to the characteristics of length of the saltating grains, but probably more influenced by the statistical fluctuation in the scatter of these impacted grains. So, this wavelength of this is called these ripples. The wavelength of these ripples is about to 1 meter. So, this is near about equivalent or similar to that saltating effect. That means, a grain which is salted from here will move here, or saltate from here it will move here near about here. So, a grain which is saltating from here it will move here. So, this is all about your saltation and ripple development. Sand ripples are characterized by a lag concentrate of coarse grains at their crest, where the finer material have been removed and finer grains in their troughs. So, here if you see these two photographs is taken from this Visakhapatnam east coast of India, and if you see this crest, this is the wind crest or the ripple crest, this is looking relatively black in color as compared to the troughs. So, not only the coarser particle will occupy the crest, the heavier particle also occupy the crest, and here from the crestal part I have taken some of these sand particles, and you see not only the coarser remnants are there, but these dark color minerals are there, they are the heavier particles, the garnet, the silmanites, those are the heavier particles are there. So, that means these wind ripples at this crest, it is occupied by coarser particles and heavier particles, and at the trough it is occupied by smaller particle or the finer particles or the lighter particles. So, if you see here in these photographs, this wind is removing the material from this dune crest, and finally, the dune crest or this ripple crest, if you individually ripple crest we imagine, the individual ripple crest will occupy by the coarser particles, the finer particles they are removed here. Because of the rather low angle of impact of saltating grains, each ripple crest receives more than the average number of saltating impact and creates a shallow zone of fewer impacts and lee side of the troughs. Now, you see here this is the figure and this is the figure, you see this is the low angle of impact, this is the low angle of impact. So, maximum impacts occur this side, and as it is coming relatively in wind shadow, here less number of impact will be there. So, that is why we are getting here less number of only the free fall of the material from the crest to trough, free fall of material, but mostly impacts they are on the stoss side. This is called lee side and this is called stoss side. So, stoss side it imparts maximum number of impact as compared to lee side. Here at the lee surface avalanches occur, that means here impact is more and here impact is less. So, due to this more impact, this grains will transfer from here to here, and finally, once it says the crest due as removed finer material is removed from here, the remaining coarse material that avalanche here, and this is called the avalanche surface or the brick points. So, brick point where the avalanche occurs. Under stronger winds, the surface of a sand patch or loess is rippled form because less side shutting takes place. Then the entire surface layer is sheared forward by saltation and surface creeps. Now, see, suppose we have a sand sheet, we allow the wind to transport. So, that wind will after a particular wind speed, the grain picks up and saltation starts. Under stronger winds, the surface of sand patch loses its rippled form because less side shutting takes place. Because when we are talking about the ripples, we are talking about the size, larger grains at the top and smaller grains at the bottoms. So, it is particular wind speed is confined, but if we are increasing the wind speed, this type of arrangement will not there, it will totally mixed up. So, then the entire surface layer is sheared forward and by saltation and surface creeps occur. So, that means we are pushing this upper surface by this, because we are not able to distinguish them, the whole system, the whole irrespective of its size, the whole system we are stressing it. So, this is the effect of shear. So, what happens? However, under such conditions, new sand is also trapped from the upwind source and the sand sheet is not eliminated, but increases in area and thickness. As long as an upwind sand supply it is available, it is forms sand dunes. So, that means more and more the wind speed, more and more sand we are adding. So, that is why here we are not going for selective pickup, that we are creating some troughs, some we are creating some ripples, some trough of the ripple or this crest of the ripple. So, that the whole system without distinguishing the grain size, the whole system shears off. So, once it whole system shears, more and more sand is added, the thickness of the sand is increasing and the size increasing, and the whole system once it is moving shearing, it forms the sand dune. So, sand dune it is the larger form than the ripples. So, on this dune surface we can create ripples, we can see ripples. So, we are discussing about the sand ripples. The ripples, as we know that these are formed in the gentle wind condition. Here at the top surface it is occupied by the larger grains and the heavier grains, and this bottom or the troughs it is occupied by smaller grains and the lighter grains. So, once this wind speed is increased, so this grain size distinction is vanished. So, that means the whole total system irrespective of its size shape, irrespective of its light and heavies, the whole system moves as a shear movement. At the surface, due to the shearing effect, the whole system moves forward and creates the sand dunes. So, large accumulation landforms, wind blown sands are called sand dunes. Large accumulation landforms, here accumulation takes place, larger in size, thickness is more, length is more. So, this is called sand dunes. But once this wind speed decreases, so this movement or the migration of the dune ends there. So, in that case on this dune surface ripples again dominate, ripples again form and ripple starts migrating. So, dunes are distinctly larger and stable of or growing landforms. Even larger scale complex and compound dunes are called dras, complex and compound. That means, here interaction of more than two dunes may occur. So, this system is called dras. Here is the photographs of two dras system, a huge dunes. If you see the scale, if you take this tree as a scale relative to that, how big is that, how height wise big is that. This is called larger dunes or huge dunes are called dras. Now, you see, although ripples have the coarsest sand on their crest, on dunes the coarse grains creep or roll to these troughs and the finest sand remains at the crest. Ripples and dunes, this is the difference. At the ripples, the coarsest grain or coarser particle remains at the crest and the finers at the trough. But in the dune is concerned, here these coarser particles they will finally roll down to these troughs, and this why the cross beddings forms and dune migrate from one place to another place. This gentleman which is a pioneer worker in this wind geomorphology or the Aeolian system, it was Bagnold. In 1941, he classified sand accumulation under 5 headings. What are those 5 headings? One is sand shadow and sand drift, sand shadow and sand drift. Then second is dune, third is wallback or gibber dune, fourth undulating fixed sand sheets, and fifth sand sea or org. So, all those landforms they are associated with sand, not gravel lags. So, depending upon their size, depending upon the shape, depending their distribution, that means dimensions, these terminologies has been used to classify the deposited materials. First, let us discuss about the sand shadow. What is sand shadow? Shadow means behind something. It is whenever wind velocity is checked by a fixed obstruction, that means here wind is not blowing freely, a fixed obstruction is there. Obstruction may be a rock body, may be vegetation, may be tree. So, whenever the velocity is checked by a fixed obstruction, sand may strike the obstruction and then fall at this windward base, or be swept into the lee side of the obstruction and accumulate as a streamlined mound. So, now you see, suppose this is the wind direction and this hill is the hillock is the obstruction. Here this due to this obstruction, this sand is accumulating here, and this accumulated sand may be blown at these sides to this lee side of this obstruction, and these landforms are classed as sand shadows, because this sand accumulation occurs due to the obstruction, not due to change in velocity itself. So, they are fixed in form and size by size and aerodynamic shape of this obstruction. What would be the size? The size of this sand shadow, that will be depend upon the size of this obstruction. If it is a small tree is there, this obstruction will be less. If it is a larger mound is there, the obstruction will be more, or the sand size will be more. So, that depends upon. Now you see here some bush is here, and due to the bush we are creating a sand shadow here, a very small size, but if a large mound is there, we are creating a sand shadow here, it is larger in size. So, that depends upon the size of the obstruction. Then sand drift. Drift is are the accumulation in the lee of a local high velocity zone between obstacles. Suppose we have one obstacle here, another obstacle here. This obstacle means we have checked velocity, here obstacle means we have checked velocity, but in between these two obstacles here we will be high wind velocity, high wind speed. So, here deposition occurs due to high wind speed, this is called sand drift. So, that means sand drifts are accumulations in the lee of a local high velocity zone between obstacles. Most commonly they accumulate downwind form from a place where wind is funneled through a gap at a higher than average velocity. Now, see, these are the gaps, these are the gaps. Similarly, if these vegetations are taken as obstructions, within that vegetation these are the gaps. This is a zone of vegetation, similarly this side will be zone of vegetation, and this is the gap. So, those deposits within that gap, the lee side of this gap, it is called the sand drifts. An important side of the sand drift is at the foot of a downwind cliff or escarpment. For example, if here let us see, this wind is blowing in this direction and this is the cliff. So, whatever the material is removed by deflation, this material transported material, because here this area, this is relatively low velocity, it is calm and quiet, wind is there and wind is blowing here. So, that will deposit here, the material will deposit here. So, this is a best place to form a sand drift at the foot of a downwind cliff or escarpment. Sand blown off the plateau surface sinks into the still air in the lee of this cliff. You see, this is the still air. So, due to the still air, this blown off material from this plateau surface, it will be deposited here. When such sand drifts grow large enough, they begin to trail off downwind from the base of this cliff, and an image of this Martian surface and on the photos and electronics image of the terrestrial deserts, sand shadows and drifts are collectively called wind streaks. So, here the wind dynamics has to be understood. This upper part we have larger wind speed and we have removed material from the plateau surface, but in between these valleys at this cliff surface we have relatively less dynamics, that means stagnant wind will be relatively less, that means this velocity will be less here, it will be stagnant wind. So, this material which is removed here, it will be deposited here. With more and more accumulation, we will get a elongated sand body here, that is wind drift is there. So, mostly in the Martian surface we will find these type of sand drifts. Then sand dune continues. The true dune can be best regarded as the deformable obstruction to airflow. They are free to move, divide, grow and shrink, but they are not dependent on the fixed obstruction for their maintenance. So, the sand drifts we are talking about, that is dependent upon the obstruction, but here the dune itself its own obstructions. Here no external obstruction is required to create a dune. So, that is why true dune can be best regarded as deformable obstructions to airflow. So, that means here it behaves its own obstruction and it migrates, you see they are free to move, divide, grow and shrink, but they are not dependent upon a fixed obstruction at all. So, they can divide, a dune can divide, a dune can grow, a dune can shrink, so dune can spread. So, depending upon the wind, depending upon the sand supply, wind dynamics, this dune may deform. There are two basic principles critical to dune formation. What are those? One is the sand supply and another is the wind velocity or wind speed. The first principle is that free sand patch larger than 4 to 6 meter likely to increase in size and thickness and thus becomes a mound or hill. Why this 4 to 6 meter? Because when we are talking few minutes back, we are talking about this critical size. The critical size, that means after that or beyond that size deposition takes place, otherwise only the removal of the material will be there. So, that 4 to 6 meter critical size is required for the depositional features in the sand system or the desert system. So, the first principle of formation of the sand dune is that if the free sand patch larger than 4 to 6 meter is likely to increase in size and thickness and thus becomes a mound or hill. And the second principle is that like a cliff, a dune develops a lee side pocket of low velocity airflow and it promotes deposition there. So, here this is a lee side and this is touch side. Here you see sand moves up windward side, that means here erosion and in the touch side here relatively calm and quiet air will be there. So, that means once the calm and quiet air will be there, whatever the material is being transported from this place, that will be deposited here, it will slide down here and forming deposition. So, these are the two principles. One is the critical size of the sand should be there and transportation or erosion takes place from the touch side and deposition at the lee side. As soon as the mound or hill of sand grows to moderate size, it develops the classic dune asymmetry of a gentle windward slope and a steep angle to the slip face, it is called lee side. It is a asymmetric geometry. Here we have gentle sloping touch side and steeply sloping lee side is there. The sand on this windward slope is firm and compact, but it blows over the crest and cascades down at the slip face. So, this side it is dangerous for a geologist because this sand system is loose. So, it may happen that these casualties may happen here if you do not properly understand this dune dynamics. Here this side this sand is compact because shear force is there, that means hard and compact, it is compressing the system, but here it is a free fall. Free fall means there will be empty space, more empty space, more pore space will be there. So, this part it is very dangerous for a geologist which is actively involved to study the dune dynamics. The internal structure of a dune is fixed by original deposition and slight compaction, whereas the dune form may move with or without changing the shape. The internal structure is immobile. Now, you see in this particular figure it is shown here. Suppose it is the earlier position of this dune. Now, dune is migrating from this position to this position, again it is migrating from this position to this position. So, that means here you see the position is changing, but the internal structure whatever the cross bedding was here, this cross bedding was here, the ripples are on the surface, that is remain same. So, that means it may change with or without changing its shape. The shape sometimes may like this or sometimes may like this. So, that means during this movement its shape may change, but its internal structure, internal configuration is remains same as it is. So, a dune migrates from here to there. So, its internal structure will be remain as it is, however, this shape may change, its position may change. So, here this internal structure remains constant, this dune may migrate from one place to another place, its shape may change, its size may change, but this internal configuration will remain same. So, I think we will stop here and we will meet in the next class to talk about the dune classification, what are the different types of dunes, how the wind dynamics, the sand supply, the vegetation that affect this dune shape and size. So, I stop here. Thank you very much. Thank you again.